Hello, once again. Thank you for joining us. This is Space Nuts, where we talk astronomy and space science every week. And it's episode 320. And you know what that means? It's the one that came over after 319. Yes. And it's actually, coincidentally, it's the one that comes before 321.
Oh, gosh.
At least for this particular moment in time. Speaking of which, we are answering questions entirely today, although we've got one little thing we'd like to talk about called Artemis One. You've probably heard of it. But Duncan is asking about space-time. Fenton is asking about the ice on Europa. Martin One we'll call him, wants to know about the moon. Sandy is asking about minor objects. Gareth wants to talk about why light is so slow. And Martin, too, has a question about black skies. That's all to come on this edition of Space Nut.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me, as always, is my good friend and astronomer-at-large, Professor Fred Watson. Hello, Fred.
Hello, Andrew. Good to see you again. And I'm very intrigued by your new device.
My new toy.
Yes,
yeah.
new toy.
I'll put it for the people who watch the podcast on YouTube later. That's my new toy. It's a Rodecaster 2 Pro, and basically it enables me to do everything through the one processor and hopefully glitch-free. But it's got all sorts of it's got all sorts of gizmos in it that I am really looking forward to playing with, like this. That'll wake you up.
Yeah.
And
I didn't think I was asleep until you did that.
and plenty more. So, we'll have some fun with those. How you been?
Very well, thank you. Yes, all good. Sadly, Marnie has not been very well. Oh. She had an accident at Pilates on Friday. Hit the ground very hard on her face. So she's got 2 black eyes and a lot of holes around
Pole
her
dancing is really dangerous.
I thought it was something different, but no, you're right. No, it's part of some contraption that you use in Pilates. You can tell I never do any of these things, where you basically sort of pulling yourself around by your own weight, and it uses handles with pulleys, and apparently Marnie let go of a handle that she shouldn't have done, with the result that she found herself approaching landfall, kind of re-entry, coming down to Earth very quickly and landed on her face, which has not done her any use at all.
Ooh, no. Yo, pass on our regards.
I will.
It's only by coincidence that Judy has been unwell the last week or two, so that's another thing we're dealing with. But fingers crossed everyone will be better soon.
I hope so. She's it's a shame because she's got black eyes, which I worry about in case anybody thinks I've been punching her in the face, which I haven't. But what's even
against black skies.
Yes. What's even more of a worry is that she starts a new job in 2 weeks. So,
well, they're going to have a high opinion of you, aren't they?
Exactly. Quite so. Yeah.
And those bruises take a long time to.
Yeah, they do. I know. It's a worry.
Away.
Yeah. She's going back to.
Sorry, go on.
I was just going to say she's going back to her old trade.
What exactly?
Which she gave up 23 years ago. She's going to be cabin crew again.
Oh, wow.
Yeah.
Really?
She is.
Gosh.
With a well-known Australian airline that I won't mention. But yes, she's going to be cabin crew.
Oh, that's lovely.
Isn't that great? I know, I'm thrilled.
I'm
thrilled. I think it's
plenty of jobs around at the moment.
There are, that's right. Yeah, you could probably be a flight attendant as well if you wanted, Andrew. Fed up a radio.
I don't think I could do it.
I don't think I
work
could.
So hard. I just haven't got that in me, working hard. It's just not a thing. Now, before we get to our questions, we better talk about Artemis One because, everything was looking optimal till it wasn't, and it looks like a fuel leak has forced them to scrub the launch.
No, not really a fuel leak. It was a more subtle problem than that. Andrew.
Ooh.
So the launch was scrubbed. It's not aborted as such. It's postponed. They stopped the countdown at T-minus 40 minutes, I think, last night, our time. So what happens, you've got this amazing SLS, the Space Launch System, consists of basically one of the fuel tanks that used to be used on the Space Shuttle. It's something like that. It's slightly bigger, but that's why it's orange, the same colour as the Space Shuttle fuel tanks were orange. And they've coupled that to old Space Shuttle engines. This is a recycling job, but there are 4 of them rather than 3 on the shuttle. And those, they're Rocketdyne engines, have very considerable thrust. And they have to be conditioned before the launch starts, before they're lit up. Because the first thing they're going to feel, the engines, is the hydrogen and oxygen fuel coming in, liquid hydrogen, liquid oxygen. And the liquid hydrogen is at minus 253 degrees Celsius. And, you get that on your skin, you know about it, as do the metal engines. If you don't bleed it in beforehand, a slow supply of this stuff coming in to get the engines at the right temperature. And engine number 3 never got to its correct temperature. And that's why they aborted the launch. I think they've had this problem before, and it sounds to me, like a sticky valve or something of that sort that's not bleeding the liquid hydrogen correctly. So it has been postponed. The next window is on Friday this week, our time, Friday the 2nd, might even be Saturday morning. It's 2 a.m.
It would be.
Yeah. So for the second attempt, if that fails, it'll be the 5th of September. And what's interesting is the reason why they can't go any sooner than Friday, Andrew, is because if they went today or tomorrow, the spacecraft would find itself in the moon's shadow on its way out to the moon, and a phenomenon called an eclipse, and they wouldn't get any sun to the solar panels.
Oh, right.
So that would stop things. So so next Friday's hopefully go for launch then.
Yeah. They haven't got much of a window, though, have they? I think I heard that they've got to do this within a 22-day time span. Is that right?
They do. Actually, if they don't get it on Friday, then Monday's the next one. Failing that, it's the middle of October, because it's all about the moon being in the right place, and all of that stuff has to work out. You can't just say press the button anytime.
Yeah, I know. I've heard that there's like 50,000 people there to watch.
Yeah, there were.
They're going to be jilted.
Yeah, I think they were a bit upset about that. But you can't help that. And, of course, it's part of the process. As the NASA administrator said, his words were, everything has got to be exactly right before we light the candle.
Exactly.
And I never knew they used candles on those things. I always thought there was a button you could press.
That's what all that sparking is underneath when they're about to ignite the engines. Well, it's candle power.
Candle power, yeah.
That's what it is.
Some of the...
I mean, I've been reading up on all the things that they're going to be doing on board the spacecraft when it's finally up there. I mean, they've got stuff stuck on the outside of it to read radiation. They've got stuff on the inside to test various parameters. They've got other machines that will be doing surface readings from the moon. And look, there's a lot going on. And there
is, lots of science, as well as, the 3 mannequins on board. Moonikin, what's his name? I've forgotten his name. That's terrible. Compos. No. He's basically a human figure which is festooned with sensors and radiation detectors and things. It's named after a gentleman whose first name I can't remember, but his second name was Compos, Compos, I think it is, who was the engineer, the electrical engineer, who worked out how to get the Apollo 13 astronauts back to Earth safely.
Right.
So, played a very important role in the Apollo 13 saga, and so he's commemorated by having this mannequin. Sadly, the other 2 are female figures who seem to be devoid of any limbs, which makes them a bit unattractive, I have to say. But but they've got the important bits there, I think.
Oh, that's good.
And then there are Lego figures, and of course there's a Snoopy, and a Shaun the Sheep as well.
Sheep.
Yeah, Shaun the Sheep from Nick Park's Hardman Productions. Oh, it's
Fantastic.
It's fantastic. So they will all be waiting to go as well.
Yeah, fingers crossed. Yeah. We wait with bated breath, but not happening as yet. Maybe tomorrow, as the case may be.
Tomorrow, as of recorded time for this.
Yes, or release date.
Yes, release date. That's it.
Yeah, we have a launch of 1800 hours Thursday.
Okay. Right.
I don't know when he does it, but anyway. Right, let's go to some questions. And first up, this one from Duncan in the UK.
Hello, it's Duncan here in the UK from Weymouth again. Another question, this time about space-time. Can you please explain what space-time is actually made out of? I understand people say that there's various quantum fields and all that sort of thing, but space-time is bent by masses that sit in it, such as the Earth, which explains gravity and all that. But if it's bent and if it's expanding, then space-time has to be made out of something. But what actually is it made out of, other than just such vague terms as a quantum field? So, is it made of atoms of something or some other fundamental particle? Just what is it? Can we get hold of it and put a lump of it in the jar? I'm just interested to know what space-time actually physically is. Okay, keep up the good work, and I'm interested to hear what you have to say about this. Thank you. Goodbye.
Thank you, Duncan. Always great to hear from you. You always ask insightful questions, and the answer is blue tack. It's not blue tack?
That's near enough. Duncan's already on the money. He's saying, how could you put it in a jar? Well, it's in a jar already.
Yeah.
And the jar is in it too. So, look, it's, I guess and I understand where Duncan's coming from, of course, because at one stage in the history of humankind, scientists thought that space was filled with something called the ether, which basically was the medium which transmitted light radiation. It was before they knew about radio waves. This was in the late 19th century. So the ether that was a comfortable way of imagining space. You had a medium through which light could travel, and it was exactly analogous to the Earth's atmosphere through which sound travels. Sound has a medium, although sound's a compression wave, and they already knew that light is a transverse wave, more like the way a guitar string vibrates. But that whole idea got thrown in the rubbish bin by two scientists, Nicholson and Morley, two professors. Actually, I think one of them was they may even have both been military guys. I have to look back at that because it's a long time since I've written about Michelson and Morley. But they had something called the Michelson-Morley experiment, which used light itself to determine that there isn't a medium that light travels through. So, and that's because light, they found the velocity of light is invariant, which is the fundamental prospect of relativity. So that threw out the idea of there being a medium that transmits light. And in a sense, that threw out any idea of something you could bottle, to put it in Duncan's terms, that there isn't anything. Now, Duncan's absolutely right in that space is full of stuff. And I'm reading here from Wikipedia because I can't think of this list. It's a near perfect vacuum, of course, but it's got this low density of particles in it, a plasma of hydrogen and helium, electromagnetic radiation, magnetic fields, neutrinos, dust, and cosmic rays. So all of that is in space, and they are small amounts. There's 5 to 10 protons per cubic centimeter in the interplanetary space. That's the space between the planets, and there's all the stuff in space. That's the point that I'm trying to make. But that's not space itself, and that's the thrust of Duncan's question. And the answer is, and once again, I'm reading from Wikipedia because it puts it absolutely succinctly. Space-time is a mathematical model that combines the 3 dimensions of space and 1 dimension of time into a single 4-dimensional manifold. They don't say Riemannian manifold, but that's what it is. So it's really a mathematical model of the structure of the universe. But we know that mathematical model behaves in certain ways. Exactly as Duncan says, you put a mass in it and it will distort it. That's because it's a 4-dimensional manifold. It'll change its shape. So that is the best answer that any physicist can give, because there isn't another one. There's nothing that says, yes, it's something like the ether. It's nothing like the ether. It's simply a mathematical construct which works extraordinarily well and fits what we observe. More than that, we do not know.
So we live inside a mathematical puzzle.
Yes, we do. And that's led some people to think that we're actually, we're a simulation of some sort, that we're not real, that we're... In fact, didn't you write about that in one of your fevered imagination books? It's probably the basis of the Matrix as well. I can't remember what the Matrix is about because I never watched this stuff.
Well, the Matrix is about people, living in a construct, but they're actually in the real world. They're being fed on by machines.
Oh, okay. Oh, that's nice. That's yes.
Good
anyway,
thought, isn't it?
It is, yeah. But notwithstanding that, if we are part of a simulation, then that suggests that space-time should be quantized. In other words, it should go in tiny, tiny steps rather than continuous, just a continuous movement. And so if ever we discover that time, for example, is quantized, then we'll know we're in a simulation and that you and I aren't real. We're just a mathematical model.
Yeah, that's scary. I think they have done movies like that. I think actually Vanilla Sky, which starred Tom Cruise, had that kind of element to it, but it turned out, well, I don't know. People like my movie and TV show recommendations, and if I blow the whistle on how this one ends, it's not going to be much fun. But I do recommend it. It's pretty old. Yeah. It got panned by the critics, but I liked it. I enjoyed the concept. But basically, Tom Cruise plays a character whose life is unraveling. Yeah, and when he finds out why, that's the twist in the story. But I can't. I won't blow it. I won't blow it for anybody. But do you concur with the Wikipedia analogy?
Yeah, it's what that's how we deal with it in the world of astronomy and astrophysics.
Wikipedia.
No, as a mathematical construct. It's what all the whole thing about distortion of space and time, gravitational lensing, the whole deal comes out of that. Well, it's general relativity. That's the basis of it all, which is quite extraordinary. One mathematical model that's proved so accurate and so predictable, and that it seems to be it's not the answer to everything, though, because we know that relativity and quantum theory are not compatible at the tiniest scales. All
right, more to learn. But Duncan, there's your answer.
Yeah,
could be blue tack, could be mathematics.
But whatever it is, you've got it in a jar already. So put it on your shelf, label it space time, and you're there.
Just sit there quietly at night looking at it. It might a penny might drop, especially if it's a jar full of pennies. Okay, thanks, Duncan. Let's move on to our next question from Fenton.
Yeah, hello, Fred and Andrew. This is Fenton in Minnesota. It's in the morning for you. I know that it's a little bit before 3 o'clock in the morning. So I have a question for you about the ice on Europa and how also that relates to the sulfur dioxide with which the surface of Europa is being bombarded. So if we go outwards from the core of Europa, we've got the we've got the water, then we've got the relatively pure congulation ice, and then on top of that we have the frazzle ice, which has a high concentration of salt, and then on the surface of Europa we've got sulfur dioxide with which the surface is being bombarded. So should that mean that there is an electrical potential that runs from the core out to the surface of Europa? Yeah, anyway, I hope this is something to keep you thinking. Up all night. Bye now.
See you later, Fenton. Thanks for the question. Europa's ice is not simple, is it, really?
No, it's not. And nice to hear Fenton talking about frazzle ice, which we were discussing
about
last week. That's right, yeah. So he's right that it is complex and there is sulfur dioxide on the surface. I can't remember how it was detected.
A sulfur dioxide detector?
Well, you could probably do it spectroscopically with a sulfur dioxide detector, yeah. Anyway, doesn't matter. Was it Juno? I don't know. But it's one of the things that is going to be, focused on by the Europa Clipper, NASA's spacecraft due to launch the year after next, 2024. So, so you've got a surface of water ice, but also sulfur dioxide on top of it. And I think Fenton's question is where does it come from? And I think the answer is not actually known, but the external origin theory is the one that really has the most impact, because we know that Io, the biggest moon, the nearest of the Galilean moons to Jupiter, is spewing out sulfur all over the place. That's where the sulfur comes from, and probably sulfur dioxide too. That it's there's probably chemical origin for that. So and those particles actually find their way to Jupiter itself because of the magnetic fields. The particles that come from Io are channeled by the magnetic fields of Jupiter and constitute the radiation belts of Jupiter. But there is something called the Io footprint near, I think it's Jupiter's, it might be both of Jupiter's poles, but I've certainly seen it marked on Jupiter's south pole. And that's where the stuff coming from Io actually lands on the planet's cloud belts. So it's not out of the question to think that Europa, which is kind of going the other way, but that Europa's still bathed like the whole of the inner part of the Jupiter system, bathed by sulfur dioxide ions probably, and that might be where it's come from. So that's it's a question that's not yet properly answered. And maybe the Europa Clipper will give us the answer, but that's the thinking, that yes, it's just because of the particle content of that whole region, a lot of it coming from Io itself, that we've got this sulfur dioxide on the planet's surface.
Io is a messy place.
It is, yeah. It's just a disaster, really, isn't it? It's, when you look at images of it, there's yellow stuff all over, which is sulfur. Volcanoes going off willy-nilly. And all because it's so close to Jupiter that it's being squashed and squeezed in the gravitational pull of Jupiter.
Yeah, sounds like the average city on Earth, basically.
Yeah. Well, Sydney's better than that.
You reckon?
Yeah. There's not many sulfur volcanoes around here.
I avoid it like the plague, I must say.
Yeah, you don't know the best bits, that's why.
Oh, okay.
Come and see us next time you're in Sydney.
Yeah, well, you're in the best bit.
We are.
Yeah.
Yes.
National parks all around you.
We do,
Nice.
that's right. Yes, it's lovely.
All right, thanks, Fenton. The answer is we don't know, but it could be IO's fault.
Yeah.
And thanks for the question. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson. Let's take a break from the program to tell you about our sponsor, NordVPN. Now, I've talked to you many times about a virtual private network and the advantages of having one. And it is true. A lot of people don't need convincing, but it also comes down to the quality of service, and you'll get no better than NordVPN. They are the leading service. They can block trackers. They can check downloaded files for malware. They can just make sure that your whole system is not being infiltrated, whether that's by hackers or by opening an attachment to an email that you probably shouldn't have. And they're highly backed. A lot of big organizations believe in this product, and so do we. Now, if you're a Space Nuts listener, you get a special deal, which I'm going to tell you about in a moment. But, there are all sorts of situations where you're exposed to problems online, such as hackers and viruses, whether it be at home through your email service or through using public Wi-Fi. All of these things can put you in danger. And with NordVPN, you can protect up to 6 devices at once, from your smart TV to your smartphone to your computer, you name it. And it's as simple as just joining NordVPN and downloading the software. But at the moment, there is a special deal for Space Nuts listeners. Now, all you have to do is go to the special URL that's been set up, nordvpn.com/spacenuts. There's an exclusive deal, the NordVPN Cyber Security Package, all inclusive, plus 4 months free. That is a fabulous deal and pretty simple. Other advantages, of course, you access the global internet, you get shielded from cyber criminals, and you can secure all those devices I was talking about. But there are extra layers of security when it comes to protecting your digital interests. The Nord Pass, the password manager, and the Nord Locker, which is a file encryption tool. So you can get all that in one easy package at a very low price with a 30-day money-back guarantee. You can try it risk-free. So log on to nordvpn.com/spacenuts. Use the code word spacenuts to get that deal with that extra 4 months free. That's nordvpn.com/spacenuts and use the code spacenuts. Now, back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
All right, we're going to just slam straight back into the questions, and this one comes from Martin.
Hi guys, it's Martins from Latvia. I had a question about moon's gravity effect on Earth. So I know that moon affects our water levels on Earth, like we have tides rising and falling, all that stuff, in the rivers and lakes and so on. But is it possible when moon's up in the sky, either at night or in the evening or in the day, I can jump higher, or it doesn't work like that? I mean, maybe not such a drastic difference like in centimeters, but maybe in millimeters, like I can jump higher when the moon's gravity is helping me or so on. But anyways, yeah, I was curious about that one. Anyways, guys, I've been listening since 2017, and yeah, please never stop, and take care and bye-bye then.
Thank you, Martin. This sounds like a Latvian conspiracy leading up to the Winter Olympics, in my opinion. But
maybe so. It's
if they time it right, they might be able to do a record ski jump because the moon's in the right place.
The right place.
Yeah,
it's a lovely country, is Latvia. We were there a few years ago with a tour. Took a tour group up there and part of one of our Aurora tours, and had a lovely train journey through the snow, because we always go these things in winter. And of course, lots of tours of Riga, the capital city, which is full of marvellous architecture. It's a stunning place. So you're very lucky, Martin. And the answer is no. No, it's not quite no. So the bottom line is we're on the surface of a planet which is gravitationally pulling us downwards. The moon is indeed up in the sky and has enough gravitational pull to affect the tides, exactly as Martin says. But the moon's mass is only 1/80th of the Earth's mass, and it's 384,000 kilometers away on average. So its pull is very, very slight. And in fact, what causes the tides is the difference in the pull of the moon from one side of the Earth to the other. That's actually what it's all about. It's about the fact that you've got a body that has liquid on both sides, and one side is nearer to the other, so it feels more of a pull. You're smiling. I guess your grandchildren have arrived.
My grandchildren have just come home from school, and yes, they're being their usual quiet selves.
Well, I can't hear anything, so they're doing very well.
I would not put long odds on them bursting in any second.
All right, that's all right. Yep, we'll see how that goes.
Question: what are you doing and why?
Yeah. Can we join in? And what are all those buttons there?
Can I push? What's this button for?
Yes, quite. So my guess is that if it affects you at all, it'll be in terms of microns rather than millimeters or centimeters. It's an interesting thing to ask, though. A great question from Martin. I probably should do the calculation, but I can't do that one in my head, unlike the barycenter one, which I did.
It could just make the difference at an Olympic Games high jump or pole vault if the moon just gets in the right place at the right second in the process. You just don't know.
You don't know, and it might only take a micron. That's right.
Yeah, could be enough just to stop, just to get someone over the line or over the top or whatever it is they do in those sports, which I've never, ever been very good at. Never tried pole vault. Did high jump at school. I wasn't very good at that. Did javelin. Wasn't very good at that. Did shot put. Just was total crap at that, basically. When it came to athletics, I was sorely lacking. It's not my forte.
Mine neither. Although I did for a while aspire to such things, but only for a short time.
Yeah.
Until I realised I was useless.
I don't know if it was because I was bad at it or if it's because it was something they forced us to do at school and I didn't want to. Motivation goes a long way to success, I think.
Indeed. So sorry, Martin. It's a great question, but I think the answer is very, very little indeed.
Yes, no moon assist for your Winter Olympic jump, I'm afraid. Thanks, Martin. Let's get closer to home with Sandy in Melbourne.
G'day, Fred and Andrew. It's Sandy here from Melbourne, Victoria. Hope you're both well, and thank you for bringing us this great show. My question today is around various objects such as minor planets and asteroids in our solar system. With the exception of comets and objects smaller than what we're currently capable of detecting, have we mapped all the various objects orbiting the Sun? Is this a known quantity, or do we only have an idea of objects above a certain size? And the second part of my question is there professional telescope projects actively trying to build a comprehensive map of our solar system, or do we already have that? Thank you.
All right. Thanks, Sandy. And I've seen some of your wonderful photos online in recent weeks. Sandy took a really good photo of Saturn, which I saw published. I think I only saw it published this morning on his Instagram page, and he explained how he did it. I think it was a 2-minute exposure or something to that effect. But really good job. He's very clever, is Sandy. Minor objects. We did talk a couple of weeks ago about that. A fellow, a scientist or an astronomer, who said we really need to start looking at objects inside Earth's orbit of the Sun, which could include these. But define a minor object, I suppose.
Well, that's right. And so Sandy raises an interesting question in the sense that he's kind of put his finger on the answer already. So we know everything above a certain size, but below that size, and that's probably probably. Well, okay, I've got to qualify this because we're really talking about near-Earth objects here. Near-Earth objects above 1 kilometre in diameter, we think we know 95% of them because that was what NASA was mandated to do. And they're big ones, so they're relatively easy. But they wouldn't be easy if they were in the asteroid belt. You wouldn't be able to see them at that sort of distance, except by an occultation, like the one that was used to discover that Trojan asteroid's moon that we talked about a couple of weeks ago. Yeah, Polymele, was it? Many sheep, the name of it.
Yeah, that's the one, I think.
Anyway, yes, it depends whereabouts in the solar system you are. If you're in the near-Earth environment, we probably know pretty well everything above 1 kilometre in size. But you can then calculate from that, because you know the distribution of objects above that size, you know how many there are of a certain size, and the numbers fall off as you go bigger until you get to the biggest asteroid series, which is 1,000 kilometres in diameter, give or take, 900, I think. So you've got a spectrum of the size, the number of objects of any given size, and so even below the 1 kilometre or so that we know about, 1 kilometre and above, when you get to that level, you can extrapolate the curve. So you can statistically deduce how many objects there are of a smaller size. You just don't know where they are for the most part. A lot of them you do, because they've found huge numbers of these things now. But the answer is, we probably never know a complete map of the solar system if you want to include things below a few kilometres. It's because again, you've got the problem, if you start thinking of the Kuiper Belt way out there beyond Neptune, it's only objects that are a couple of thousand kilometres that you're going to see, like Sedna, which is 2,000 kilometres across. Pluto's 2,000 kilometres across. These are objects that you can find because they're big, but there'll be other objects there that are a couple of kilometres in diameter. Look at Ultima Thule, for example, or Arakoth as it's known now, the object that New Horizons spotted after it went flying by. That's, I think, 30 kilometres or something. And there'll be millions probably of objects of a similar size, but spread over vast areas of space, and at such distance that we're never going to find them.
That's a pity.
Yeah. But there are telescopes that are mapping the solar system in the sense that they're discovering new potentially hazardous objects, among others, and that process continues. So as soon as anything's found and its orbit is calculated, which needs 3 or 4 observations, the more the merrier, then you've essentially mapped it. You know where it's going to be.
All right, I'm confident that we're okay because Sandy's on the job.
Exactly. There you go.
Yeah. Very, very keen sky watcher is Sandy. Knows where everything is and catalogues it accordingly, I reckon. So, Sandy, no. To use the Australian vernacular.
That's right. Yeah, no. Never understood that.
I don't either. I never use it until now. But thank you, Sandy. Lovely to hear from you. Hope all is well in Melbourne and that you're staying drier than we are. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Space Nuts.
We might as well just keep rattling on, Fred, and see what the next question is about. This one comes from Gareth. He's concerned that light is too slow.
Ah, yes.
Hi, Fred and Andrew. Gareth from Brisbane here. Absolutely love the podcast. Thanks for bringing the amazing universe to my ears each week. My question: why is it that when we observe distant objects in the universe that are relatively close to the Big Bang, circa 13 billion years ago, why is it that the light is only reaching Earth or the James Webb Space Telescope now? Wouldn't everything have been much closer together in the past? And wouldn't we have expected this light to have reached Earth earlier, given the universe, I assume, is not expanding anywhere near the speed of light? I hope that makes some sense. Thanks again for a great podcast. Love it. Cheers, guys.
Oh, can I do it? Can I?
Yeah, go for it.
I think the universe is expanding. beyond the speed of light.
It did, certainly, yeah.
Yeah. It still is, isn't it? Otherwise, I don't know.
So you've got to work out what you mean by that, because
the expansion of the universe is accelerating.
Yes, but the speed at which it's expanding depends on how far apart objects are that are being carried away from each other, and there may well be bits of the universe that are being carried away from us faster than the speed of light, but they're beyond the horizons that we can see. In fact, that itself makes a horizon, and eventually that's what will happen with the accelerated expansion of the universe. There will be objects whose light can never reach us.
The journalist in me just wanted to tip water on Gareth just then, and I think I just flicked him with a drop or two.
No, you did. The word to use.
No offense, Gareth, but it sparked my brain.
The magic word that you should have been using there is inflation. Because that's when the universe did expand faster than the speed of light. It expanded by a factor of about 10 to the 50 in something like 10 to the minus 33 of a second, which is, that's just a colossal thing. And we just simply don't understand that. The observational evidence is there. It's been accepted since the early 1980s that the universe immediately after the Big Bang, the universe underwent this expansion, fantastic expansion, superluminal expansion, you could call it, because it's faster than light. Of course, it doesn't affect the speed at which light can travel through the universe, but the universe itself is whizzing faster than the speed of light. So that's why. I'm not sure. Let me think back to Gareth's question.
Well, he's asking essentially why we're seeing the light now.
Why we can still see it. Yeah. And it's because because the universe is so big. That's the bottom line. It's so big that it takes stuff a long time to get here. And Gareth's quite right that the universe was much more compact at the beginning, but after the period of inflation, which was effectively the beginning, it was a lot bigger than you'd think it was. So it's not as though everything was compressed together.
Okay, I still can't quite get my head around it. So it happened cataclysmically fast, and inflation happened. Everything went everywhere, and then after inflation, what? We just kept expanding.
It's kept expanding. Yeah. So if you look at diagrams, Andrew, of the way space has changed shape over the history of the universe, and they've got to be.
Sorry, that's my phone. People ringing me at inappropriate times.
Yeah. These have got to be cartoons, of course, because we can't see the universe from the outside, because there isn't an outside. But what you've got with the accelerated expansion is a kind of trumpet shape. It's giving the universe a trumpet shape.
Oh, okay.
But it doesn't start off from zero. It starts off with inflation. So it's like a fat trumpet, the shape of the universe, if you can think of it that way.
It's kind of like this.
Yes, that's more or less it. Yeah. That sums it up pretty well. In fact, it's got everything in there, a bit of inflation at the beginning as well.
I couldn't help myself.
No, I knew you'd
got my new toy.
Find a use for that.
You opened that door.
I did open the door, yes, not intentionally, but I opened it. So I think inflation's the kind of secret that is required for Gareth to get his head around what's actually going on.
Right. Okay. Wikipedia, Gareth.
You could always try Wikipedia, which is very good.
If you do a search for inflation in Wikipedia, though, you'll end up in some political group.
Yeah, you would. That's right.
You were going to say?
I was going to say inflationary period. It's if you look up inflationary period or thereabouts in Wikipedia, I'm sure you'll find something about it.
All right. Yeah, everything's been bouncing around ever since, and so some of the light continues to reflect and refract and ends up back here.
Still on its journey. The thing's, yes, it's getting bigger.
Yes, indeed. All right. Thanks, Gareth. So nice to hear from you. Let's go now to Martin. He's got a very interesting question for us.
Oh, space nuts. Martin Berman Gorvine here from Potomac, Maryland, USA. Writer extraordinaire in many genres. With a blue sky, or rather a black sky question for you. If the force of gravity were somehow to cease suddenly, how quickly would the Earth lose its atmosphere? And would we all die quicker from the disappearance or floating off into space of the air and I guess the crumbling of the Earth itself, or from the plasma and stuff from the sun coming apart hitting us? Love your show, guys. Can't wait for the answer. Berman Gorvine out.
Thank you, Martin. I love what-if questions. So what's he asking? If
gravity stopped.
Gravity stopped. Okay. Yeah, we'd get flung off, wouldn't we?
Well, it's a complex thing. So the first thing is the Earth would sort of suddenly start going in a straight line rather than sticking with the sun. The sun would indeed start swelling, and there would be plasma. The solar wind, which takes travels at 1 million kilometres an hour or so and takes 3 or 4 days to get here, that would certainly change as the outer atmosphere started becoming part of the solar wind, the sun's atmosphere. But we'd be long gone before that, because not only would we become weightless, the atmosphere would also be weightless and would very quickly, so we'd suffer this very rapid loss in atmospheric pressure as we floated away. And yeah, it wouldn't be pretty, actually. And
no,
I think it would be. Just thinking about Martin mentioned the Earth crumbling, because the Earth is what made it spherical is the self-gravity. I think it would probably not want to stay spherical for long, because it's got very hot stuff inside, which probably starts trying to expand because there's no self-gravity holding it together. So there might, eventually at least there will be terrible earthquakes as the mantle tried to push up through the crust.
It's very bleak.
It will be a bleak outcome, yeah. I think it would make, what's his face drifting off into space in 2001: A Space Odyssey look quite homely, really, look quite gentle.
And the oceans, they'd just all...
Yeah, they'd start floating away as well, yes. Well, because the atmospheric pressure is dropping, so the oceans, their boiling point would fall, and eventually they'd start evaporating very rapidly, yeah.
Yeah, I don't think we'd be here for long, would we?
No, we wouldn't. I mean, it'd be nice to float away, but I think the other consequences...
Yeah, not like that, though.
No.
You want to be able to come back and go to bed at night.
You do. Well, of course, you want to have a happy ending, which...
yes, wouldn't be very happy under those circumstances.
No, not at all.
Would not be a pretty picture, Martin, but I'm looking forward to reading that book.
Yes, that's right. Might get ideas for your next one.
I've got ideas for my next one.
Good.
Just don't know when I'm going to find the time to do them.
Yeah,
because as people may be starting to become aware, we've got a second podcast now.
Yes.
With Astronomy Daily, and it's only a short form podcast, which we're doing every day. And it's early indications are people are enjoying it.
Good. That's
and
good.
Enjoying my co-host, who seems to be very witty and a bit of a smart mouth. Yeah.
Oh dear, better lift my game, hadn't I?
Oh
AI,
no.
If AI can be wittier than
No. You don't want to go there.
No, okay.
No, but look out for it. It's on the Space Nuts website, the Astronomy Daily podcast. But that most people are looking at as an add-on, and it gives them something to do waiting for this one. So
That's
that's I never expected that reaction, but that's good. So they seems they're working well together. By the way, thanks, Martin. Great to hear from you. And don't forget, if you do have questions for us, you can send them to us via the Space Nuts website, spacenutspodcast.com or spacenuts.io. There's an AMA tab at the top that enables you to send voice questions, which is always lovely to get. Or you can send us a text question or an email question if you like. And on the right-hand side, there's another button that says send us your voice question. We're not being subtle about that, obviously. Two ways of sending voice, one way of sending text. We don't mind either way. We'll take either. But please keep them coming in. We do love to hear from you. We're going to finish up for another week. Fred, thank you so much for spending some time with us.
Oh, it's always a pleasure. No, it's good fun. And amazing milestone, 320 of these.
Yes.
So let's look out for the next 320 and see how we go.
Indeed. Yes, indeed. We'll be back next week with 321. In the meantime, don't forget to leave reviews on your favourite podcast distributor. And if you've ever considered becoming a patron, you can do that on the Space Nuts website as well. Okay, that's where we're going to leave it. Thanks, Fred. We'll see you soon.
Take care. Bye for now.
You too. Bye-bye. And from me, Andrew Dunkley, thanks for listening to another episode of Space Nuts. We'll catch you next time. Bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.